welcome to the course structure analysis. I am Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So far we have seen 13 lectures and we started the moment distribution method. We discussed about what is meant by moment distribution method, and then we derived the distribution factor for one end is fixed, other end is simply supported, and both the ends are simply supported. What is the carryover factor? So in today's lecture we are going to discuss about the distribution factor. So this carryover factor, stiffness factor and distribution factor is part of the procedure for the moment distribution method. So without that we cannot able to solve the continuous beam by using the moment distribution method. So lecture 14 we are going to discuss about the distribution factor, and at the end of the lecture student can able to understand the concept of the distribution factor in moment distribution method for solving the continuous beams. So what is mean by distribution factor? Distribution factor is the ratio of rotational stiffness of a specific member to the rotational stiffness of the overall all the members connected at that joint. Okay. So by seeing the definition, it's a bit difficult to understand. So I'm going to derive the distribution factor. At that time, definitely you can able to understand what is mean by distribution factor. Okay. So quickly I'll go to the derivation. Okay. So I'm going to take a fixed beam. I'm going to take a fixed beam, and then which is hinged with the another beam. Okay. So two beams is crisscross in nature, in between the hinged support is there. Let's give some name for this: A, B, C and then D. Now in order to derive the rotational factor, distribution factor, it is the ratio of moment applied and then the moment produced. In simple terms, it is the ratio of moment applied and then moment produced. Let us say this center point is O. So we have the members OA, we have the members OB, OC and then OD. For all these members we are going to derive the distribution factor. Now what I am going to do, I am going to apply a clockwise couple at the point O, in the hinged support O. So let us say the applied moment is mu. Let us say applied moment is mu. So because of this moment, the beam is going to deflect like this. So it's not exactly like this, because near the fixed support, we may not have the deflection. So let's simply modify this curve slightly. So it's going to be here like this, because at the fixed support the slope is 0. Then all the way it's going to deflect like this, and this case it's a simply support. Now what are the various properties of this members? Let's write it here. Members, we have the member OA, OB, OC and then OD. What are the moment of inertia for these members? The moment of inertia for member OA is I1, OB I2, OC I3, OD I4. Then the Young's modulus. So for OA E1, OB E2, OC E3 and OD E4. And what about the length of the span? We consider all the members having different span. So L1, L2, L3 and then L4. Okay. So if I write all these things in the diagram itself, it looks very clumsy. That's why I have put the table and then I have written all those things. Okay. So then we are going to mark the important parameters, that is a stiffness. Say the member 1 having the stiffness of K1, OA, and OB having the stiffness of K2, OC having the stiffness of K3, and OD going to have the stiffness of K4. Now, in last lecture, we have discussed two important parameters. One is the stiffness factor for a beam when one end is fixed, other end is simply supported. We derived from the equation the stiffness is 4EI by L. Okay. When both the supports are simply supported, we derived the stiffness is 3EI by L. So in our case, if you see, member OA and OC is one end is simply supported, the other end is fixed support. But if you see OB and OD, both the end supports are, we say, simply supported. Okay. So from this, I am going to write the equations. For example, we have OA, OB, OC, and then OD. Member OA corresponding stiffness is K1 and OB corresponding stiffness is K2, similarly K3 and then K4. So what is a K1? So member OA, one end is simply supported, other end is fixed. So that is 4EI by L. So E1, I1 and then L1. Coming to the member OB, so OB is a simply supported. So for this, the stiffness is 3EI by L. Okay, so I2, E2, L2. Once again for member OC, if you see OC, O2C, one end is fixed, other end is simply supported. So again 4EI by L, I1, E1, L1. And for K4, 3EI by L. So E1, I1, oh sorry, this to be 3 and this has to be 4. Okay. So E3, I3, L3 and this is E4, I4 and then L4. Okay. Now I am going to compute the total stiffness. So the total stiffness equal to K, which is the summation of K1, K2, K3 and then K4. Okay. Now what is the moment applied at the point O? Moment applied at point O. The moment applied at the point O is mu. This mu is nothing but K theta. I will tell you why mu is equal to K theta. Because stiffness is equal to moment required to produce the unit rotation. Okay, stiffness is equal to moment required to produce unit rotation. So here the moment applied is mu. So mu by theta is equal to K. Okay, so mu is equal to K theta. So this is the total stiffness. This is the total stiffness. Mu is nothing but the total stiffness. Now I am going to calculate the stiffness of all the members and then I am going to calculate the moment distribution factor. First of all, moment distributed. Okay. So for the member OA, we are going to have the value mu1. So mu 1 is nothing but K1 theta 1. So member OB, we are going to have a mu 2. So the corresponding moment is K2 theta 2. For member OC, applied moment, distributed moment is mu3. So, this is K3 and then theta 3. So, for member OD, it's mu4, K4 and theta 4. So, these are the distributed moment. So, total moment is K theta. From that, K1 theta belongs to member OA, K2 theta is OB, K3 theta distributed to OC and K4 theta 4 distributed to OD. Now, you need to understand one thing here. The theta is not a variable. So, theta is a same value. In that case, there won't be any theta 1, theta 2, theta 3. Stiffness is going to vary according to the length, according to the cross section and all. Okay. So, I am going to now calculate the distribution, moment distribution, okay, or distribution factor. So, what is that? The moment distributed divided by the moment applied, moment distributed divided by moment applied. Okay, so what is the moment distributed? Distributed moment is mu1 divided by applied moment is mu for this case, and for this case the distributed moment is mu2, applied moment is mu. For this case the distributed moment is mu3 and applied moment is mu. In this case the distributed moment is mu4 and then applied moment is mu. So, let us calculate. Mu1 is K1 theta and then mu is K theta. Mu2 is K2 theta and mu is K theta. Mu3 is K3 theta and mu is K theta. Similarly, mu4 is K4 theta and mu is K theta. Now, if you see the theta will be get cancelled in all the terms. So, I will be going to have K1 by K, K2 by K, K3 by K and then K4 by K. What it represents? This is K4 by K. Actually, what it represents? These are the distribution factors. These are the distribution factors. So, the distribution factor is for the member OA, K1 by K, member OB, K2 by K, OC, K3 by K and OD, K4 by K. So, in this lecture, we are discussed about the distribution factor, what is mean by distribution factor, how to derive that. In the next lecture, we are going to see how to apply this distribution factor in the numerical problems. So, we have seen what is mean by distribution factor. Next lecture, we will see by applying this distribution factor how to solve the problem. Okay. So, thanks for watching this lecture. Thank you.